Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 787, cheapest flight within K stop. This is a medium level difficulty graph problem. We're told that we're given n cities connected by some number of flights, and we're given an array of flights where each element in flights has three sub-elements: from, to, and price. So the source, destination, and price. And this indicates a flight from city from to city 2 with a cost of price. So we're told that we're given three integers: source, destination, and k, and we need to return the cheapest price from source to destination with our most k stops. So what can we take into this problem? Well, this problem has a couple of factors which will allow us to ascertain which kind of algorithm we need to use to solve this problem. The first clue is we have a source and a destination. So we have a source and destination node that we're given. So let's say in this example, source is 0 and the destination is 3. So we're trying to go from 0 to 3. So we have a source and destination. We also have prices, so how much it costs to get to these cities via a flight. So these are our weights. So what does this tell us straight away? Well, we need to go from path A from our source and destination to our destination, to our end destination, and we need to do this, find the cheapest path, and then these prices are basically weights. So this is a classic Dijkstra's algorithm that we can use here. However, there is a there is a caveat, and that caveat is the fact that we need to do this in k amount of stops, without most k stops. And so in a previous video, in the last video actually, I solved this problem using breadth first search, specifically, breadth first search with a min heap, which is, in essence, a modified Dijkstra's algorithm, and we factor in stopping, factor in taking into consideration at most k stops. And our solution, it takes a while to come up with, and it's the most kind of intuitive solution. If you're solving this problem, it's what you would think first. Another solution is the Bellman-Ford algorithm. So that's Bellman-Ford. And Bellman-Ford is basically a iterative, stage-by-stage algorithm which is designed for this kind of problem. So it takes in, there's different implementations of Bellman-Ford that we can do, but for the solution, we can, just like Dijkstra's algorithm, we can put in a source destination and a end destination, as well as it takes in the maximum amount of stops, which is going to be k. And I definitely recommend reading up on this algorithm. And basically, we want to do k plus 1 iterations on our graph, and we want to, in linear time, find the cheapest price from a source to a destination with our most k stops. And Bellman-Ford is amazing to solve this kind of problem. So I'm going to go over a quick overview of Bellman-Ford. However, I definitely recommend reading the pseudocode and looking up the algorithm for yourself, because it makes a lot more sense when you do so, and it's probably not going to make the most sense at first glance. So let's actually walk into how Bellman-Ford works. So let's create a sample graph. Let's say we've got three nodes, A, B, and C. So to go from, it's a singly directed graph. So from A to C, and then from B to C. Okay. And we have weight. So let's say, I don't know, we have a weight of 100 here. From B to C, 100. And then from A to C, 500. Okie dokie. So let's look at the cheapest path. So let's say, for example, we need to do k plus 1 iterations. Okay, we know that much. And we know that k, let's say k is 1, so at most 2 iterations. So let's say k for this graph is going to be 1, and that's the maximum amount of stops we can take. So, the first solution we could have is from A to C, which is 500. But this is we can do better than this. We can go from A to B, and then B to C, and this is only one step stop. This is only stopping at B, and this gives us a total of 200. So this total is going to be equal to 200, as opposed to the 500 over here. We don't want the 500. We want the 200 because this is more optimal. So how do we actually try to solve this problem? And again, this is where I definitely recommend looking into pseudocode and the theory of Bellman-Ford, because there's a lot more than I can explain in this video. But in essence, we want a hash table, and we want to store each node at a number of how, of the cheapest price so far for each node. So let's say we have A, we have B, and we have C. Okay, so for A, the initial price is going to be equal to 0, B is going to be infinity, and C is going to be infinity. How do we solve this problem? So we do something called relaxing edges. So if you once you read the Bellman-Ford theory, you'll understand that relaxing edges in essence basically means the maximum is basically the maximum amount of vertices we can take. So relaxing edge basically mean the distance of vertex, or basically updating the best known distance to a vertex if a shorter path is found. So a path from one node to another, we relax that edge, so we find a shorter path for a distance to that vertex. So how would we do this for k+1 iterations? Well, the first of all, we have infinity. So we set all our nodes to infinity apart from A, because we know that the distance from A to A is from our source to source is just going to be a 0, so we don't need to do anything. So we set A is going to be first set to 0. B, well, to get to B is going to be 100, and to get to C, is going to be 500 initially. Because we can go from B to C. And however, what about from A to C? What about from B to C? Well, B to C, we don't do anything here, because if we don't look at the current mutated hash table, we look at the previous hash table. So this hash table here, and B is set to infinity, and infinity plus 100 is still going to be less than 500. So we don't do anything here. So, we leave C at 500. So on our next iteration, we set A to 0, A to B, well, that's going to be 100. And now we look at our previous iterations hash table. And in this hash table, 100 is going to be path from B to C. So we can update this new path to 200. So this should make sense. So we will do this for k+1 iterations, and we will relax edges until we find our result. And then we can simply return 200 as our result. Let me tie that up better, because that is not how one should type result up or draw it. So that's going to be our result, 200. So I hope this this basic overview of Bellman-Ford makes sense. And again, I do recommend you guys don't just follow this video, but also look at the theory behind Bellman-Ford. So let's actually solve this problem. We want to create our hash table first, which is going to be a list of infinity floats times by n. And remember, we want to set the source destination equal to 0, because the distance from source to source is just going to always be 0. And then we're going to say for I in range of k+1 iterations, and this is unique to Bellman-Ford, so it's going to be k+1 iterations. We want to relax all the edges. Before we do that, we want to create a temporary prices hash table, so that we don't mutate our mutate our source of truth. We create a new copy for this specific iteration, and we say prices dot copy. This will create a deep copy. And what do we do now? Well, we say let's actually go through all the flights. We'll go through, all the edges. We're going to say for S, D, what is it for? From, so source, destination, and price in flights. If the source destination is equal to float infinity, well, then we can just continue. We don't want to relax this edge because we got infinity as per our theory. Otherwise, if prices of S plus P is less than temp prices D, what we can do here is say, let's set temp prices D. So let's set our destination temp prices D equal to prices of S plus P. So that's our inner loop done. And then we can set prices equal to temp prices, or temp prices. Yeah, we can use temp prices, just pass it in like that. And what we can do next is then say we're going to return -1, because we're told that if there is no such root, we return -1. So we return -1 if prices destination is equal to float of infinity, which means we did not find a flight from a cheapest flight from source destination with at most k stop. So we're just going to return float infinity. Otherwise, we can return prices destination. Let's run our code, guys. Let's check that this code works, and it does. Let's submit our code. And we pass all 58 test cases. So in terms of time complexity, guys, we're looking at an O of n. Let's draw this. So O of n times E, or yeah, we can say O of n times E, where E is going to be the number of it's going to be the outer loop. So it's going to be the number of E flights, and the inner loop, which is going to be this loop here, is going to be n, which is basically going to be n is going to be equal to k plus 1. Space complexity wise, we are only really using a Python list. So space complexity, well, we are creating prices and temp prices arrays. So I'd say, yeah, space complexity is going to be big O of n. So big O of n space complexity. And that theory checks out. So with that being said, I hope you guys enjoyed this video, and I'll catch you in the next one.